Now that we know that we can do reactions with acid chlorides, we should know how to make one. The easiest way to make an acid chloride is using carboxylic acid with thionyl chloride, or SOCl2. In this reaction, the oxygen lone pairs will come in to form a double bond, and these electrons actually will attack the sulfur and kick those up. So we formed a new bond here. This is positively charged. This oxygen formed a bond with sulfur, which has an O-, Cl, and Cl. That sulfur now has a good leaving group on it, so these electrons can come back down to reform that double bond with sulfur and kick off a chlorine. We reform the sulfur-oxygen double bond, and also we kicked off that chlorine minus. That Cl can pick up that proton. Now this part of the molecule is a great leaving group. So another molecule of Cl- can attack here. The lone pair from the oxygen can come down and kick off this wonderful leaving group. And we get the acid chloride. Plus SO2 and Cl-. Reactions that we can do with acid chlorides include hydrolysis. We add water to that, we'll get a carboxylic acid. If we add an alcohol to this, we form an ester. This will act as the nucleophile, electrophile. Here's my leaving group, and you'll form the ester. We can make amides with acid chlorides in an aminolysis reaction. An acid chloride with ammonia will give us a primary amide. If you have two equivalents of a primary amine, we'll get an RH, so a secondary amide. We'll need two equivalents with the secondary amine. So this is an easy way to make an amide. We can also reduce it using excess lithium aluminum hydride, as we have before, to form the primary alcohol. And if you want to make an aldehyde using an acid chloride, we can use a bulky reagent. So lithium aluminum hydride has 4 H's attached to it. If you have one H here, plus a big bulky group, which would be these tert-butyl groups, we can make the aldehyde. So this is a bulky lithium reagent that stops at the aldehyde. So previously we used a Grignard with an ester and it would make a tertiary alcohol. A Grignard with an acid chloride will also get us the tertiary alcohol. And 2 additions of the R2. This is our nucleophile, electrophile. So these mechanisms are all very similar. R2, O-, this is our tetrahedral intermediate. Those electrons will reform the double bond and kick off chlorine. Chlorine is now gone, and I have this ketone, which we know reacts with Grignards. We add acid, pick up that proton, and then we get the tertiary alcohol. A Gilman reagent is another nucleophilic organometallic reagent. This also reacts with acid chlorides. The difference here is that the metal is copper, and we use lithium instead of magnesium and bromide. And also, this only adds 1 equivalent of the R group. So this one stops at the carbonyl. Whereas the Grignard will keep going. So the Gilman reagent, which uses the copper and lithium, that will stop at the carbonyl. So now we have all these reactions that we can do with the acid chlorides. You probably didn't even notice that. If you started with the carboxylic acid, we use thionyl chloride to make the acid chloride. Adding water and pyridine will bring us back to the carboxylic acid. If you use an alcohol with pyridine, that gets us the ester. An amine, either ammonia, primary or secondary, will make us amides. Lithium aluminum hydride can reduce it to the primary alcohol. The bulky lithium aluminum reagent will give us the aldehyde. Excess Grignard will give us the alcohol, that's tertiary, and then the Gilman reagent will give us the ketone. So we can think about what reagents you could use here to do these reactions. In order to make the acid chloride from the carboxylic acid, we use SOCl2. To form a secondary amine, we just need 2 equivalents of this. And this one we're creating a carbon bond. This is going to be a ketone, so we don't want to use the Grignard because that would make the alcohol. So we want to use the Gilman reagent. So it's copper or lithium. And this will have 2 R groups on it, only one of them get delivered. All right, so acetic anhydride can be made using 2 moles of acetic acid at very hot temperatures. This is 800 degrees. This process doesn't really work for most other acids because their structures can't stand the high temperatures, but for whatever reason it works with acetic acid. So the more practical synthesis is to use an acid chloride with a carboxylate. So if we have this acid chloride here, we attack it with a carboxylate. You can see the arrows here. The O- will attack here. We're going to form the tetrahedral intermediate. So everything just came along here. We have an O-. Then we have a leaving group here. These electrons will come back down, kick off that chlorine. And we have the acid anhydride. These are slightly less reactive than the acid chlorides, but they're still very reactive. These are often used to acetylate an amine or an alcohol. So this is the acetic anhydride. It can be used to put this part of the molecule onto the alcohol. Or you can do that with the amine. So this reaction we actually did in lab. You used salicylic acid with acetic anhydride to make aspirin. So there was a carboxylic acid. And the alcohol got acetylated. This is para-aminophenol, and we can acetylate this nitrogen, which is more basic. And this is the structure for Tylenol. And that's just acetylating that nitrogen. So these are reactions that you can do with acid anhydrides, which are very similar to the ones that you can do with the acid chloride, because the reactivity is just slightly less. To make an acid anhydride, we would use the acetate. To make the acid anhydride, you would take sodium hydroxide to make the acetate, and then add an acid chloride to get this anhydride. If you add water to that, that will get you the carboxylic acid. Adding an alcohol will make the ester. The amines will get you the amides. You can reduce it to the alcohol or the aldehyde, and you can also use Grignards and the copper lithium, because again, this is acting as the same as the chloride, which has a good leaving group. To make an ester, we use a Fischer esterification. This is going to combine a carboxylic acid and an alcohol using an acid catalyst. So methanol is the alcohol that we're going to use to make the ester. Carboxylic acids are not great electrophiles. So to make it a better electrophile, and methanol is not a great nucleophile, so we can protonate the carboxylic acid carbonyl to make it a better electrophile. Having this here will increase the rate 1 × 10⁶ times. Methanol will be our nucleophile. That will be positively charged. And our goal here is to get rid of one of the OH groups. So we're going to do a proton transfer. So this proton here will shuffle onto the alcohol. And now we have a good leaving group. So these electrons can come down, kick off that water, and we lose water. Dye is protonated, so we just do a proton transfer. And all of these mechanism arrows are actually reversible. So they've done labeling studies with this reaction. If you have a carboxylic acid with the OMe, you end up with this O-methoxy group here. So we can use the carboxylic acid with acid and an alcohol to make an ester. We can also use an alcohol plus the acid chloride to make an ester, which we've already seen. Reactions that we can do with esters include saponification. That is an aqueous hydrolysis using base. And in this reaction, we form the carboxylate. This is how soap is made. Okay, so ester hydrolysis can also be done under acidic conditions. The carbonyl of the ester is protonated and then water acts as a nucleophile. In this case, the OH- can act as a nucleophile. The hydroxide here can attack the carbonyl. We will expel this as a leaving group. Once that carboxylic acid reforms, another molecule of base will deprotonate that carboxylic acid to give you the carboxylate. We can do aminolysis, which is making the amide with that ester. So the mechanism for this will be the same as the acid chloride and the acid anhydride. You end up with the amide plus methanol. This is a slow reaction. There are better ways to make amides, especially using the acid chloride or the anhydride. We can reduce esters using lithium aluminum hydride, which we saw in earlier chapters. So we get the OH plus methanol. That's with excess lithium aluminum hydride. And we can also reduce them to the aldehyde using diba. That one stops at the aldehyde. So this is a bulky aluminum reagent, just like we saw earlier with the lithium, that will stop at the aldehyde. So the diba stands for diisobutyl aluminum hydride. It's also sometimes written as di-bal-H. We can react the ester with the Grignard, which we also saw in the alcohol chapter. This you would need excess followed by acid. Just like with the acid chloride, we're going to get the tertiary alcohol with the addition of 2 of those Grignard groups. So the esters are not as reactive as acid chlorides or acid anhydrides. So if we wanted to look for reagents to get these products from this lactone, which is a cyclic ester, in this one here, we're breaking off ethanol and this carbon chain here. This is 1, 2, 6. So we're not going to be losing any carbons. And we have a bunch of alcohols, so we're probably doing a reduction. I would use excess LAH, or lithium aluminum hydride, followed by water. So this ethanol here is from here, the reduction of that alcohol. So this is going to get cleaved off when we reduce here at that carbonyl. This will become an alcohol. This is already going to be an alcohol when that one gets cleaved off. So we have 2 carbons. That's going to be the 5 and 6 here. So this carbon 1 is going to be this carbon right here. And then we'll get that with the excess lithium aluminum hydride. In this case, we're also forming 2 things, and so I noticed that I'm gaining carbons here, and it looks like there was not methyl groups here before, but now we have a whole bunch of methyl groups. So I think we're adding CH3 MgBr in excess, followed by H3O+. So the Grignard can react here. To give us these 2, and it can also react here to give us these 2. So this got added, this got added.